Welcome to EDU World Space.
Okay, so we're doing chapter 32, problem 54. So this says a parallel beam of light containing two wavelengths. We have wavelength 1 of 465 nanometers. The second wavelength in the light is 652 nanometers. These have respective indexes of refractions in the silicate class of 1.642 for the 465 and 1.619 for 652 nanometer light. So they both enter an equilateral prism, and we want to figure out what angle does each beam leave at. So let's draw our prism here, this being 60 degrees. Okay, so if we enter in here at an angle theta A, we will then leave at an angle theta B, which means we'll enter this one at an angle theta B. C, sorry, we already did B. And then we'll be leaving at an angle theta D. So we want to figure out what theta D is for each light. Okay, so first let's figure out what theta B is for each. So we know, let's write that Snell's law first. We know that the in air sine of theta A equals in I for whichever light ray we're thinking about, sine theta B I. Okay, so if we solve that for theta B I, this will be the inverse sine of NA over NI times the sine of theta A. Okay, so theta B1 is the inverse sine of 1 over 1.642 sine of, what did it say it entered as? Oh, it entered at 45 degrees. Let's write this over here. Theta A equals 45. So 45 degrees. And that means for the first light, so for 465 nanometers, we have theta B1 of 25.51 degrees. For B2, we'll plug in the same things with a different index of refraction. We get 25.90 degrees. Okay, so now we got to use geometry to figure out what theta C is. So if we look at this top triangle, call this angle B, angle C, we know that 60 plus B plus C must be 180. So this is 60 plus 90 minus theta B plus 90 minus theta C equals 180. If you solve that out, we see that theta C comma I, and this is given as 60 degrees minus theta B comma I. Cool. So let's go ahead and find the C for both of these. So C1 and C2. C1 is 60 minus 25.51, and that is 34.49 degrees. C2 is 60 degrees minus 25.9, so this comes out to 34.10 degrees. Okay, so now we know theta C for both light rays. So the last thing is to set up our last Snell's law, which means in I of sine theta C I equals in air sine of theta D I. So we have theta D1, and this is the inverse sine of n1 sine theta c1. If we plug what our n1 and theta c1 is and then plug that in our calculator, we can see that this is 68.4 degrees. Okay, so now let's do theta d2. So this is our answer for the first ray. Our theta d2 here is given as the inverse sine of n2 sine of theta c2. And this, if you plug everything in, should come out to being 65.2 degrees. So since these are about 300 nanometers apart, once they go through this, they're going to get each deflected about a difference of 2.8 degrees away from each other.